We're now going to begin Chapter 18, Energy and Work for Rigid Bodies. Now, given that the energy equation was developed in the previous course, Engineering 1082, we're not going to go through that process. We're basically just going to have a quick review of the elements of the energy equation and also a discussion of what factors having rigid bodies adds to the mix, as it were. Okay, so kinetic energy. So when you have a particle, all right, something that's infinitesimally small, all you're concerned with is 1/2 mv squared for that particle, all right? Particle per se can't sit there and rotate on its axes or whatever. So all we have to do is look at the center of mass of the particle, which is infinitesimally small theoretically. It's a point mass. And we just have to apply that. Rigid bodies, we have now rotation concerns, and so now we have the following. 1/2 Ig omega squared. Okay, so we have to add this into the mix for what we are doing. Okay? Now, for fixed axis rotation, we'll take note that if we are rotating at O as opposed to G, note that Vg squared would be R from O to G omega. So we can express this as the following. So 1/2 mv squared becomes that. And of course, that's just the parallel axis theorem if we bring the mass moment of inertia G plus the R omega squared together. And so we can express kinetic energy rather than these two terms as 1/2 mass moment of inertia at the point of rotation omega squared. So that's a difference for us. Okay. Now, potential energy. This is just review. It's the same thing. The work of gravity is V1 minus V2, or PE1 minus PE2, and that's just mg of the first position minus the second position. And what do we normally do? We don't write the equation as PE1 minus PE2. We just put the PE1 on one side, the PE2, the second state, on the other. Spring work, also V1 minus V2, and it is also then 1/2 KS1 squared minus 1/2 KS2 squared. There's nothing new here. Non-conservative work. We'll just recall that relative to non-conservative work, in many cases it works out to plus or minus force times the distance that you go through, where this is distance along the path. Okay? It is plus or minus simply because if the force and distance are generally in the same direction, you get positive work. If the force goes one way and the path of travel goes the other, it's negative. All right, so we've seen that before, and we'll just recall this is the general form of the equation for work. The last thing we need to contemplate here, here's that form for the equation of work, and we'll just bring up the last thing we need to consider. How do we handle torque and couple moments? All right, that's very straightforward. You always, when you're looking at energy, it's basically something that's driving the motion going through a displacement. Okay? We see that here. So we can have force drive motion and then the displacement is this distance. If you have a torque or couple, the torque or moment is what drives the motion, namely the rotation. Okay? And the displacement is the angle you go through. And we should note this is in radians. All right. So those are the keys to doing energy problems. Beyond that, it's just the same as we had when we dealt with particles. Okay. Same basic idea. We'll note, however, that when you deal with rigid bodies, at times you have multiple rigid bodies that are part of the system you're analyzing. Well, that's no problem. Basically, for every mass or moment of inertia that we're dealing with, we will have 1K. Let's bring this down. We will have, for every mass, we have one kinetic energy term for every mass. We'll have one PE term for every mass. Now keep in mind these may be 0, but they are there inherently. All right. So that's our quick review of energy, and we'll stop the video here, and we're going to move to problems right away. See you soon.